All right, for this example, we're going to derive the velocity field for a planar Couette flow, um, and we're going to start from the Navier-Stokes equation. So let me go ahead and sketch out what the geometry looks like. Actually, we're going to do a planar Couette-Poiseuille flow. So let me write this down. Planar Couette-Poiseuille flow. And Couette-Poiseuille, these are two different famous fluid mechanics people from long ago. So the geometry that we're dealing with is we have two parallel flat plates. So we have one flat plate on top, another flat plate on the bottom. They're supposed to be parallel here. They go on for an infinite distance in and out of the page and also left and right, and they'll be separated by some distance h here. We'll have let's have gravity acting downward here in this particular case. Between the plates, we're filling it with fluid. And let me put a coordinate system on here as well, just so we know which direction we're talking about. So we'll call that the y direction, and this will be the x direction. And we're going to solve for what the velocity profile looks like between these two plates as we change some boundary conditions. So one boundary condition that we'll consider is we'll move the top plate at some velocity off to the right. And another boundary condition that we're going to use is having both plates fixed, but then we'll also put in a pressure gradient to push the fluid through here. So I'm kind of leaving it general at the moment, but we'll simplify everything. I'll show you where these boundary conditions and the pressure condition shows up. So I want to leave it general, and then we'll make it more specific later on. So as with all Navier-Stokes solutions, we generally have to make a number of assumptions in order to make the equations manageable to solve by hand. So the assumptions that we'll make here, we're going to make a number of them, so I'm going to number them here. We're going to assume that the flow is parallel, or I'm sorry, planar. So planar flow. And what I'll do is I'll state in words what it is, and then I'll state in mathematics what I mean by that. So a planar flow means there are no variations in the z direction. So the ddz of any quantity is going to be 0. We don't have any variation in and out of the page, and at best, the z component of the velocity will just be a constant. It could be 0 or just a constant. We just want it to be a planar flow. All the actions really happening in the xy plane here. The second assumption we'll make is that we're dealing with a steady flow. So it's not changing with time, so that means ddt of anything is equal to 0. The third one that I'll assume is that the flow is fully developed in the x direction. Let me write it down and then explain it. Fully developed flow in x direction. What that means mathematically is the velocity components in the x direction are 0. The gradients of the velocity components in the x direction are 0. So what it means is that the x velocity and the y velocity don't change as we move in the x direction. I'm not worried about the z direction because it'll be at most a constant, so it's automatically 0 as well. So what that means is as I move left or right here, the velocity profile will look identical. And that's a pretty reasonable assumption. If these plates are infinitely long, there's nothing, whether I look at the plate here or look at the plate over here, it looks exactly the same. There's really no identifying feature that anchors down where we are in the x direction. You'd have no idea if I drew it over here or drew it over here, you'd have no idea that I was to the left or the right. It looks exactly the same as you move in the x direction, so there's no reason why the velocities would have any dependence on the x direction. Okay, and then item number 4 is that the only body force acting is in the y direction. So gravity only acts in y direction. That was just part of the setup of the problem. So g sub y is just minus g. Okay, so I've numbered these assumptions because I'm going to refer to them later. And by the way, the approach I'm taking to solving this problem is one that I recommend. It's good to to specify what your geometry is, and then what assumptions you're making. And then what we'll do is we'll simplify the continuity equation and the Navier-Stokes equations, and then we'll make use of these assumptions. So I'll refer back to them by their number. Let's first start with the continuity equation. We know that for any flow field, we have to always satisfy conservation of mass, or the continuity equation. So for this planar flow, oh, I guess I should make another assumption in here as well. Let me do that before I go on. Assumption number 5 is that we're dealing with an incompressible, and I'll also say constant dynamic viscosity fluid. So what I mean by that is that the density is a constant and the dynamic viscosity is also a constant. Okay, so getting back to the continuity equation, this is just conservation of mass shrunk down to a very small control volume. So for our incompressible flow, it'll look like the following. So this is what continuity looks like for an incompressible fluid that's planar. We don't have to worry about the dz term because that one's 0 because it's planar. And since it's incompressible, this is what it looks like. All right, so if you look at this for a moment, we can use assumption number 3 here to say that dux dx is 0. So that's 0 because of number 3. And I think this is a good way to simplify things. You say this is 0 and indicate y. It goes back to number 3 here. Okay, that way you're communicating how you're solving the equations a little better. So then we're left with dy dy is equal to 0. Well, we also know dy dx is 0. That's from number 3. We also know dy dz is 0 because it's number 1, because it's planar. So at best, uy is a constant. So using the continuity equation and number 3 and number 1, as well as number 2, that it's steady. We know it's not a function of time either. We know at best uy is equal to a constant. Because just in general, let me write it down over here. Uy in general could be a function of x, y, z, and t, right? Well, we know it's not a function of x because it's fully developed in the x direction. We know it's not a function of y because we just found that from the continuity equation. We also know it's not a function of z because it's planar. That's up here, number 1. And we know it's not a function of time because it's steady. So at best, it's going to be a constant. So how would we find that constant? Well, we can go back and use a boundary condition. You see we have these solid walls here, right? So there's no flow through the walls. So since there's no flow through the walls, that means that constant has to be a 0. So the uy has to be equal to 0 everywhere. So I'll just make a note here. No flow through walls means that uy has to be 0 everywhere. Because it's a constant, and if it's 0 at the walls, that means it's 0 everywhere. I'm going to call that item number 6. It's not an assumption, but I'm just going to call it number 6 just so I can refer back to it a little more easily. I guess we can call it condition number 6. It's not an assumption. Okay, we could have assumed that it was 0. We could have just said that, okay, everything's flowing along in nice horizontal layers here with no y component. And so we could have made it an assumption, and it would have been correct. But I just want to point out you don't have to do that. We can actually show that it has to be horizontal just from the continuity equation. Okay, let's move on now. So now let's take a look at the Navier-Stokes equation, specifically. Let's look at it specifically in the x direction. All right, so now what we'll do is we'll write out the Navier-Stokes equation in the x direction. Initially, you probably have to look this up in an equation sheet But as you do many of these problems, you'll have this memorized ultimately. Oh, I forgot a term here. Let me use the magic of my iPad here to give myself a little more space. Look at that. Okay, so here we have uz, dux, dz. I got a little ahead of myself here when I wrote this down. Okay, so there's our Navier-Stokes equation in the x direction. Let me just describe what the terms are. This is the density times the acceleration. This is the Lagrangian derivative of the x component of the velocity. So it's the acceleration in the x direction. So the left-hand side here is like a mass times acceleration. It's really mass per unit volume times acceleration. This minus dp dx, this is the net pressure force per unit volume acting in the x direction. So we have, it's a surface force. This is our net viscous force in the x direction. So that's what that term is. So this is another surface force. So this is pressure force, viscous force, and there's our, and then we have our body force, and I wrote it down incorrectly. It should be a density times gx. So there's our body force in the x direction. So this is just F equals ma. Here are your forces, surface forces, body force, and this is our mass times acceleration. And everything here is per unit volume. So let's go ahead and simplify this then. So to simplify it, we're going to make use of the assumptions we wrote down up above. So the first one is 0 because of assumption number 2, it's a steady flow. The second term is 0 because of assumption number 3, that it's fully developed in the x direction. The next one is 0 because uy is 0. That's condition number 6 we just derived. The next one is 0 because of assumption number 1, that it's planar. The dp dx I'm going to leave for the time being. The d squared ux dx squared, that one's 0, again because it's fully developed in the x direction, that's number 3. Du squared, dux squared, dy squared, that one we have to leave. There are no assumptions that govern that one. It's very easy to just start setting things to 0. You can see here 0, 0, 0, 0, 0. That's why I think it's important to put in parentheses why it's 0, because it forces you to stop for a moment and think about it. This one is not 0. There's nothing that we can say about this at this point in time. But the next one, that one's 0 because it's planar, so that's number 1. And then the last one is 0 because of number 4. Gravity's only acting in the y direction. So with that in mind, what we end up having is the following. D squared ux dy squared is equal to dp dx. And then there's a mu in front of this as well, the dynamic viscosity. Okay, so here's our dp dx. I just moved it to the other side of the equation. Here's our d squared ux dy squared times the mu right there. Now before I go any further, let me just make a comment about our ux velocity. So again, our ux velocity, like our uy velocity or uz velocity, could be a function of x, y, z, and t, right? So it could be any of those. Well, we know it's not a function of x because it's fully developed in the x direction. We know it's not a function of z because it's a planar flow. And we know it's not a function of time because it's steady. So really, at best, ux is a function of y, right? So with that in mind, we can change our partial derivative over here to an ordinary derivative. It's just a little mathematical thing that we'll make use of. It'll just make it a little easier for us to do our, solve our differential equation. Okay, so now we have this ordinary derivative. We still have our dp dx in here. So we're still assuming that there's some pressure gradient that's helping to drive the flow. What I mean by that is the pressure's changing in the x direction. If I go back up to the picture here, what that means is we could be driving the flow because the pressure over on this side, let's say the pressure over here, might be larger than the pressure over here. So let me draw a little picture over here. If we have a little fluid particle, if the pressure on this side is larger, let's say it's P plus dp dx times dx, and the pressure over here is just P, then that little piece of fluid will be pushed along, of course, in that direction, right? So a negative pressure gradient. So if dP dx is negative, meaning the pressure is dropping, dP is negative as dx is positive, means the pressure is decreasing as you go that direction, then that will induce flow from left to right. Right? It's pushing from left to right. Just keep that in mind. Okay, I should probably add some more words here. Then fluid is being pushed from left to right. Okay. Anyway, let's get back to the problem. We're going to leave that in there just in case there is some pressure gradient. This is a differential equation that we now need to solve. Okay. So let's go ahead and rearrange it and solve it. So let me just write it like this. All I did was take the derivative out here, and then I will write it like this. I'm going to take the dy to the right-hand side, as well as the mu. There we go. So all I did was take this dy and bring it over here, left this d here with this one, and divided through by the mu. So we can integrate that. We can integrate both sides, and we'll get dux dy is equal to 1 over mu dp dx times y plus some constant. I've assumed when I integrated this with respect to y that mu is not a function of y, because we assumed that it was just a constant dynamic viscosity. And I'm also assuming that the pressure gradient in the x direction doesn't vary with height y. It's the same pressure gradient at the top plate as it is at the bottom plate. Okay, so I've made that assumption here. Now we can integrate once more. Let me just write it all out. So we can integrate both sides again. Right? We can rearrange the equation, integrate once more. So we'll have ux is equal to 1 over 2 mu dp dx y squared plus c1 times y plus c2. The c1 and the c2 we'll have to find from boundary conditions. They're just constants of integration. So you can see here the ux is now looks like a parabola. Our velocity profile looks a bit like a parabola here. So now let's try to find the c1 and c2. We'll get those from boundary conditions. So let me go back up to the picture for a moment. And you see, we know something about the x velocity at the bottom plate and the top plate. Specifically, we know that we have the no-slip boundary condition at these walls. So at the bottom wall, what I'm going to do at this point is I'm going to say that the bottom wall is fixed. And let's just say the top wall moves at a velocity v off to the right. Okay, so I'm just arbitrarily setting up these boundary conditions. These are the kind of boundary conditions you would have for a Couette flow. Kind of looks like this. Okay, so that means that from the no-slip boundary condition, the x velocity when y is equal to 0 is 0, and the x velocity when y is equal to h should be v because of the no-slip boundary condition. So let's write those down. From the no-slip boundary conditions, that ux at y is equal to 0 is 0 because it's sticking to that bottom plate and that bottom plate's not moving. And ux at y is equal to h, that's at the top plate, it's equal to v because again it's sticking to that top plate. So if I plug in y is equal to 0 into here, so this will be 0, this will be 0, so we'll quickly see that c2 is equal to 0. And then if I plug in y is equal to h, and then v is equal to, ux is equal to v, we'll get v is equal to over 2 mu pdx h squared plus c1 times h. We want to solve that for c1, so we'll get the following So that's our relation for C1, and we can go ahead and plug that back in. So we'll get something that looks like this. All right, I think I've done that correctly. Let me just double check. Okay. So that's what our velocity profile looks like right now. We can clean that up a little bit. Let's rearrange that somewhat. This will end up looking like what I'm going to do is just write this term with the v separately and then gather the dpdx terms together. So we'll have a v times y over h plus an h squared all over 2 mu times dpdx times a y over h times a 1 minus y over h. I think I've done that. Oh, there's a minus sign in here. Okay. This is, all I've done is use algebra to rewrite this. I just wanted to write it in a form where I can group some terms together. And I think I've done everything correctly there. Let me just quickly take a look at it. Yeah, that all looks correct. So this is now our velocity in the x direction. So we have now derived what our velocity in the x direction is from the Navier-Stokes equation, and we also made use of the continuity equation. So it's continuity is conservation of mass, Navier-Stokes is really just the momentum equations. And we've derived what the velocity profile looks like. And it's a combination of a couple of terms. If we make dpdx equals 0, then it becomes what's known as a Couette flow. What we define as a Couette flow, and the velocity profile is just v times y over h. This is something that we actually referred to early in the course. If you recall, when we first started talking about viscosity and viscous stresses, I gave a velocity profile that looked like this. It was linear, and I just told you at the time, just assume it, but here we actually just derived it. So when you don't have the pressure gradient and you only have the moving boundary, you get this kind of linear velocity profile. It looks like this. So remember, this is moving at speed v, and this is fixed. The velocity profile just looks like that. So this is our ux velocity, and this is y. So that's what that looks like. And the other canonical style flow that we use in fluid mechanics is if we make v is equal to 0, then we get what's known as a Posai flow. So this is a flow that's driven just by pressure. So that one looks like this, h squared over 2 mu minus dpdx. It's y over h, 1 minus y over h. This is actually a parabola. So if I sketched out what that velocity profile looks like, it would actually look like a parabolic profile with the maximum at the center. So again, this is our y direction headed up this way. It's our ux velocity. And this one, remember, has a pressure gradient. So if this is the x direction heading to the right, dpdx is less than 0. The fluid is being pushed from left to right because the pressure is decreasing as we move in the positive x direction. So that's what the velocity profile looks like for what's known as a Posai flow. A Posai flow is where the boundaries are fixed, and we move the fluid by pushing it with this pressure gradient. There are 3 common ways that you can move fluid. One is to move a boundary, like a Couette flow, and that moves the fluid through the no-slip boundary condition. Another way is to push fluid using a pressure gradient, like this. That's known as a Posai flow, so we're moving the fluid just through the pressure gradient. And the third way is to use gravity. So if we had a component of gravity in the x direction, that could also move the fluid. that doesn't have a special name to it. The Couette-Posai flow combines both a moving boundary and a pressure gradient, and so that's what this one is. That's a Couette-Posai flow. It just has your Couette part and your Posai flow. So it's a combination of this linear profile plus the parabolic profile. And so depending on the magnitude of V and dpdx, you can get profiles that look something like this. Let me just go ahead and sketch one. Let's say this is a very large velocity V, and we also have a pressure gradient. You can get something that maybe looks something like that. You can see sort of a parabolic shape, and then of course it's stuck to the top plate like that. Or if the plate's moving in the opposite direction, let's say the plate is moving backwards, and this one is fixed, you could get a velocity profile that actually, and let's say the PDX is like that. It's the same in both of these, so that the fluid's being pushed in the positive X direction. So in that case, it might look something like this, where it actually reverses direction. So these kinds of more complicated velocity profiles occur for the Couette-Posai flow because you have a combination of the linear profile and the parabolic profile. But if we just say you have a Couette flow, that means the pressure gradient's 0 and it's only being driven by the boundary. If we say that you just have a Posai flow, it means that the boundaries are fixed and it's just being driven by a pressure gradient. Okay, so here what we did, I just want to recap how we solved this problem. And I think this is the way you really want to do it for any Navier-Stokes problem, is you sketch out the geometry that you want to deal with. You make some assumptions, number them for easy reference. Go to the continuity equation first to see what simplifications you can make from that. So here we just found that we could eliminate the y component of the velocity. Then you solve the Navier-Stokes equation in whatever direction you're interested in. So here all of the interesting stuff is happening in the x direction. That's the velocity we want. So I wrote the Navier-Stokes equation in the x direction, wrote out its full form, and then I simplified it. And it simplifies a lot because of these assumptions. And so I identified what assumption was being used where. Typically, when you solve Navier-Stokes equations by hand, you'll see that most of these terms will drop out. Because once, if they don't drop out, the equation just becomes too hard to solve by hand. You have to use numerical methods. You can't just do it by hand. Once you've simplified it, then it's a matter of just doing the math involved. So all of this is just math, and then you get to the fluid mechanics again, where you apply the boundary conditions. So here we use the no-slip boundary condition to figure out what these unknown constants are. So here we had 2 unknown constants, so we need 2 boundary conditions. And then we ended up with our velocity profile, and then it's always worthwhile to kind of sketch it out to see what it might look like under various conditions. Once you have your velocity profile, you can find many other things. So for example, if you wanted to find the volumetric flow rate through that channel, that's just going to be the x velocity integrated over a little bit of area. So W here would be the distance in and out of the page. dy would be, so here are our 2 plates. This is the y direction, remember. It's the x direction. So what I'm doing is I'm integrating over a little area like this, dy. We've done this many times in other problems. I'm finding the flow rate through that little area, so that'll be ux times that little bit of area. I'll just write it as dA. And then I'll integrate that as y goes from 0 to h to go all the way across the channel. And I would just substitute this velocity profile in down here and do the integral, and then I get the volumetric flow rate. I could multiply that by density to get the mass flow rate. So we could find that. If I wanted the shear stress at any point inside here, I could use our expressions for the shear stress. So the shear stress on a y face in the x direction, we know from our lecture on the Navier-Stokes equations, will be dux dy plus duy dx. duy dx is 0 because that's condition number 6, that the uy was equal to 0. And so then we could simply plug in our ux expression down into here, take the y derivative, and we'll find our tau yx. So that's how we could find the shear stress. And by the way, if you look at this for a moment, if you plug this in down here, it'll be a function of y. So the shear stress would vary with elevation in here. You'd have to be careful of that. So that this would give you the shear stress at any arbitrary y. If you were interested at the plate, you'd have to plug in y is equal to h or y is equal to 0. So anyway, so once you have the velocity profile, you can get other things of interest like flow rates and stresses. All right, we'll go ahead and end that example there, but this is a classic Navier-Stokes solution, and this Couette-Posay flow system is one that we use often in engineering models. It's a pretty good approximation for a lot of different systems, so it's handy to have an actual solution for it. Oh, actually, one last thing before I forget. I had said that the flow was fully developed in the x direction, and that ended up just telling us that the y velocity is 0. So everything's flowing in layers here. We call that kind of flow a laminar flow. So laminar flow is a topic we introduced early on in the course, but it basically means that the fluid's flowing in layers, or lamina. So it looks just kind of like that. There is no y component to the velocity. That assumption only really holds true for under certain conditions. And those conditions are related to what's known as the Reynolds number. So the Reynolds number, defined in this particular case here, we'll define it as the following. Let me write it out. Then I'll explain it. So this is called a Reynolds number. And you've probably heard of a Reynolds number before, but it's a ratio of what we call typical inertial force for a fluid particle divided by a typical viscous force for the fluid particle. And we'll talk more about this with dimensional analysis, so don't worry about knowing it all that well at this point. But this Reynolds number is defined in this way, where we have this average, u bar is the average velocity. The way you find u bar would be, we want the volumetric flow rate here to be the same if we use the real velocity profile or if we use the average velocity profile. So it would be like using u bar times h times the distance in and out of the page. So we could solve this for u bar. It'd be like u bar is equal to q over hw, and you'd find q from this expression. So this is the average velocity in the channel. So this Reynolds number, it turns out that if the Reynolds number is less than about 1500, so if you plug in your values for h and u bar and rho and mu, if you put in, let's say you're dealing with water, so you can look up the density and dynamic viscosity, and your plate's 1 centimeter apart, and you know what your average velocity is in there, and you calculate the Reynolds number. If it's less than about 1500, then it's generally a laminar flow, and our solution that we derived up here will very likely work as a good model for you. And it's because the assumption of fully developed flow and uy is equal to 0 is a good one. If it's greater than that, then if it's greater than 1500, then our assumptions would break down and our predicted Navier-Stokes solution would not be a good model. What ends up happening is when you get to larger Reynolds numbers, the flow starts to swirl around more, and it becomes more turbulent. It'll go through a transitional regime, and then it'll become turbulent. But our assumption that we have fully developed flow in the x direction, and that it's steady, and the uy velocity is 0, all those assumptions start to break down. So our prediction for the velocity profile would not work when you exceed that value for the Reynolds number. Now, why 1500? It just turns out experimentally that's kind of that's the right value. It's purely based on empirical evidence. There's no theoretical justification for that. It's just based on measurements. And I need to tell you that the 1500 is just a ballpark number. It's not an exact number. It's not like at 1499 it's laminar and at 1501 it's turbulent. It's a ballpark number, kind of a rule of thumb number. The smaller the value for the Reynolds number, the better the assumption of turbulent flow. And if it's much larger than 1500, it'll be closer to a turbulent flow. So this is just a ballpark rule of thumb engineering approximation. So that's going to be true for a lot of these Navier-Stokes solutions, is that our derivations are really only accurate for laminar flows. They're not accurate for turbulent flows. Turbulent flows, we can't really derive Navier-Stokes solutions for those because they're just too complicated. We can only really derive them for laminar flows. So there'll always be a Reynolds number condition associated with our Navier-Stokes solutions. And as I mentioned just a little bit ago, we'll talk more about Reynolds numbers later when we talk about dimensional analysis. Okay, now I think I've said everything I need to say, so we'll go ahead and end it there.